Good afternoon, everyone. Thanks for coming to my thesis defense in this snowstorm. Today I'm going to talk about my research on adaptive motion planning. I'd like to especially thank my advisor Sebastian, my thesis committee members Marshall, Sheesh, Sid, for taking time out of their very busy schedule for this talk. Okay, so let's get started with a very brief overview of motion planning. So broadly speaking, motion planning is concerned with the task of computing collision-free motions from a start configuration to a goal configuration for a robotic system. Decades of research on this topic have led to a development of many tractable planning algorithms with provable worst-case guarantees. So, one of the first milestones was Carnegie's thesis in 1988, where he analyzed the complexity of algorithms that were complete, that solved the problem exactly without any approximation. Over the next decade, as researchers started examining more complex representations of robots and obstacles, these methods got updated with more tractable sampling-based algorithms. So Lavelle showed how such algorithms were in fact probabilistically complete. If you give such algorithms enough time and samples, they will find a feasible path that one exists. And then a decade later, Caramel and Predictors developed on these sampling-based algorithms to show that they can be asymptotically optimal. That given enough time, they'll find the optimal solution. Now, in contrast, a real-world application in robotics is interested in the finite time performance of these algorithms, because the robot has to make decisions in real time while dealing with computational constraints. So now, go through some examples from my own research to highlight the challenges posed by such real-time constraints. So as you mentioned, the main focus of my PhD work has been to develop the motion planning stack for this full-scale autonomous helicopter, the Boeing unmanned Little Bird shown here. So this can fly at speeds of up to 50 meters per second. It can sense obstacles up to a kilometer away. It has to avoid these obstacles by producing smooth, pilot-like avoidance maneuvers. It also has to avoid complex no-fly zones that may suddenly crop up, and react quickly to hazards that are detected very late as it comes into land. Now, the challenging aspect of this project has been to design a robust planning module that works in all possible situations that the robot encounters. So we did a battery of flight tests over the years, which is translated to over 700 flight test hours. We flew in different environments with different dynamic constraints, avoided various kind of obstacles such as mountains, towers, wires, and trees. And as we were conducting these tests, we found that we had to constantly keep tinkering with the motion planning system to ensure real-time performance in all these diverse situations. So hence, based on a vast amount of experimental evaluation, the key observation we made is that the real-time performance of a planning algorithm varies as the scenarios vary. So this becomes a significant problem if you want robots to operate for long durations in real-world settings outside of contrived laboratory settings. So the second example arises from the years of experience of designing motion planning stack for different UAV platforms. This usually has led to a lot of repeated design effort as well as unnecessary software duplication. So there's a strong incentive for reusing the planning software across these platforms. However, once again, we found that the real-time performance of a given algorithm varies with different computational constraints, different obstacle density, different robot dynamics. So this requires either painful parameter tuning or ad hoc design choices. Now this final example shows that in some situations, even synthesizing a real-time planner can be very difficult. So consider this example where a plane damages one of its wings and can subsequently only turn left as it comes into land. How can we plan motion for such a system in real time? Thankfully, planning algorithms are perfectly equipped to deal with this. The original RT paper in 1998 shows an example where a car can only turn left. However, given a fixed time budget, the planner cannot explore all these configurations within that time. So we need a planner that focuses only on promising areas, which can be very difficult to hand design given the non-intuitive nature of the dynamics. Hence, all these examples motivate us to explore the following line of argument in today's talk. that the real-time performance of a planning system varies across problem instances. And to achieve good real-time performance, we need a motion planning module to adapt to the distribution of problems a robot encounters. This is a very broad outline of today's talk. We're going to start with the main problem formulation, the assumptions we make in the thesis, the major contributions. We're then going to talk about our approach. We will talk about three main subproblems in adaptive motion plan. Then we'll conclude and discuss some open questions. So let's start with the first part. Okay, so let's first formalize the kinodynamic planning problem that we wish to solve. So we are solving for a trajectory that is a mapping from time to state and control inputs. The objective is to minimize a cost function such as traversal time. The trajectory must satisfy some start and goal constraints. It must satisfy some dynamic equality and inequality constraints. And finally, it's constrained to lie in valid free space. Usually such problems are high dimensional, and even approximately solving this original problem can be computationally expensive. So this brings us to the definition of performance. The performance of a planar P on a problem gamma is the cost of a solution computed by the planner in a fixed time budget, which we denote as J gamma P. That function is bounded between 0 and J max. So now we're ready to define the objective of adaptive motion planning. So let P gamma be the distribution over planning problem parameters that the robot encounters. So this is different start goal constraints, this is different obstacles, different dynamic constraints. Right? So the objective is to create a planner that minimizes the expected cost in real time on this distribution. Now looking at this, we see that we run into an obvious problem. How can we tractably traverse the space of all planners to actually optimize this function? To answer this question, we will break things down into a set of subproblems. We'll first ask the question, how do we assemble a real-time planner? What are the components we need? Which of those components are tunable to get real-time performance? Having answered this, we zoom out and treat planning as a black box. So imagine we have a library of such black box planners. We ask the question, can we select planners from this library to minimize the expected cost? Alternately, we zoom into the planning box and treat it as a white box and ask the question, can we directly learn tunable planning policies to minimize the expected cost? So for example, can we efficiently train heuristic policies or edge evaluation policies? So let's take a very brief look at some categories of related work and the intersection in which this thesis resides. So the first category are a set of approaches which work on modifying planning algorithms to exploit some structure in the planning problem. So either via global search techniques or via local trajectory optimization techniques or via hybrid search methods. So the second category are methods addressing non-holonomic motion planning. So there's a lot of work in addressing the hardness of the problem, computing approximate solutions using state lattices, or even trying to solve the original kinodynamic planning problem. In third category are approaches that apply machine learning techniques to motion planning, such as predicting options, learning to divide the C-space, learning heuristics, or learning policies in planning. So our work is at the intersection of all these categories. Before we move on, we briefly touch upon the main assumptions that we make. So first, our goal is to minimize the cost on problems the robot encounters at every time step. Right? We are not explicitly reasoning about perception or execution uncertainty. What we do assume is that replanning frequently as the robot moves and perceives the world suffices. So with that, we will now state the three main contributions of this work. So our main contribution is a framework to create a robust planning module that allows a robot to fly for long durations across a diverse range of scenarios. We'll demonstrate it in this example, where we have an open field, we have a robot, we have some obstacles like some shipping containers and a pylon in the field. The robot randomly samples a mission, which is a sequence of waypoints that it has to visit as fast as possible. It then takes off, plans around the pylon, then plans over the shipping containers, finds a feasible landing spot, and touches down. So immediately after, it samples another mission and repeats the process without any human intervention. This act of randomly sampling waypoints results in a diverse spread of planning problems, which include flying at speeds of up to 10 meters per second into a pylon. We'll show how our framework adapts to these diverse scenarios by learning which planning strategy to invoke in what situation, thus solving complex problems in real time. As we can see from the trace of the robot path, our adaptive planning module enables the robot to fly Monte Carlo missions for 2.5 hours without any human intervention, covering a distance of 15.83 kilometers with speeds of up to 10 meters per second. Interestingly, this learning was completely done in simulation. We had no access to the UAV. We had no access to the test site to manually scope parameters. This adaptive planner has a mission success rate of 95.56%, which is significantly higher than a hand-tuned baseline planner, which only has 64% success. So secondly, we showed that the adaptation element also allowed us to reuse planning software across diverse UAV platforms. So we report results on 3 platforms: a large hexarotor, a full-scale autonomous helicopter, and a small quadrotor. By simply training MetaPlanner on data collected from each of these systems, we are able to share planning strategies across platforms. And this sharing actually ends up improving planning success in comparison to individual hand-designed planners. Finally, we provide a framework to directly synthesize real-time planners by learning planning policies. So on the left, we are learning heuristic policies that's allowing us to solve difficult non-holonomic path planning problems on board the robot in real time. These are problems on which standard baseline searches time out. And on the right, we are learning how to collision check to find paths with very few collision checks by exploiting the implicit structure in the world. And again, compared to baseline lazy approaches, you get significant performance improvements. Okay. So with that, we move on to the approach. So this is the approach outline. Let's start with the first question of how do we assemble a real-time planner? So to answer this, we first need to ask what affects the real-time planning performance, right? So let's start by looking at a very simple and fundamental class of problems, the feasible geometric path planning problem. So we revisit the analysis of Su, Latom, and Makwani from 1999, where they analyze a classic problem in motion planning called the narrow passage. So here X is the configuration space, a subset O is in collisions, and the remaining X free is the free space. The objective is to compute a feasible path from start to goal, such that each segment of the path is completely in free space. So for the sake of analysis, let's assume a really simple roadmap planning algorithm. Right? The idea is to create a roadmap by randomly sampling n vertices and connecting any 2 vertices if the straight line joining them lies completely in free space. We can then search this roadmap to find a path from start to goal. However, we run into a problem when it comes to these narrow passages. So the probability of sampling an edge in the passage is very small. So we end up in a situation where the roadmap is not connected. So this leads to the following question. How many samples do we need to find a path with high probability? So Su et al. Provide a very crisp answer to this question by means of the following theorem. So let 2n vertices be sampled from x free. Then a path exists with probability 1 minus gamma if n is greater than the following term. So we can see the term depends on 3 parameters, alpha, beta, and epsilon, which actually parameterize the connectivity of free space. So at a high level, epsilon measures what is the visibility of the free space, so how much a point can see around it. And alpha and beta is measuring how fast this visibility can expand. And a narrow passage has small values for alpha, beta, and epsilon, so this explains why it needs a lot of samples to find a path. However, interestingly, this analysis is not all pessimistic. It also provides a recipe for fixing the problem. So consider adding interim bottleneck points B1 and B2 at the mouth of the narrow passage. Right? So what happens is that these points link up both half of the roadmap, resulting in a fully connected roadmap. And the analysis can also explain the success of this method because adding these points implicitly decomposes the space such that each subspace has high connectivity. Right? So at this juncture, we ask, can learning play a role on even this fundamental problem to improve the finite time performance? And interestingly, the authors also seem to agree when they say that an open problem, of course, is to generate these intermediate points automatically. While this may not have an efficient general solution, it may be solvable in some specific planning environments. So we are going to build up on their intuition. So consider this scenario. What the intuition says is that to produce a feasible path quickly, we don't need learning to directly predict the samples lying on the blue path. Because this is a structured prediction problem and it's not going to generalize very well. What the analysis does suggest is that it suffices to predict these difficult to sample bottleneck points and let planning algorithms compute the actual solution via systematic search. So let's try to carry over some of these intuitions to the problem we care about. So far we've been talking about the simple case of finding a feasible path. We now turn our attention back to the original problem, where the cost of the solution actually matters. Okay. To answer this, we will first need a framework that takes the full planning problem as input and produces a solution as output. But ideally, we want a framework which we can tune to get real-time performance. And we propose to do this via the following expert planner framework. So in this framework, we essentially pre-process the original problem to get a general class of path planning problems. So this allows us to use any off-the-shelf planning algorithm which is tunable to solve such problems. And then we post-process the solution to get a dynamically feasible trajectory. So while the pre and post-processing step is domain-specific, hence the use of the word expert, the planning module is general and allows a fair deal of flexibility. So we can decompose this into two steps. The first step is choosing an implicit graph, which is created by placing vertices and defining some connectivity rules. And the second is a search method applied on this graph to compute a path from start to goal. There's a lot of flexibility in the choice of this implicit graph. So for example, one can randomly sample states, one can discretize and create a lattice, or one can create custom graphs such as visibility graphs which are appropriate for certain problems. So what defines a good implicit graph? We can try to carry over the bottleneck intuition as follows. So recall that bottleneck points were points that were hard to sample points through which a feasible path passes. So similarly, we define good implicit graphs as sparse graphs, which can be searched in finite time, but likely to contain near optimal paths. And thinking like this actually gives us a recipe for creating custom graphs to solve different problems. And we've done this in several domains. So for example, on problems with narrow passages, we've used graphs with locally optimized edges to bend through the gaps. On problems with sparse obstacle clusters, we've used sparse visibility graphs that bend around obstacles. And on problems with restrictive dynamics, we've used graphs with reachability-informed nearest neighbor functions. This naturally leads to the question, can we learn to select from a library of implicit graphs depending on the scenario? Okay, so we answered the first question by proposing an expert planner framework where we can create different planners by choosing different implicit graphs. Now that we have a way to enumerate different planners, we zoom out and ask the question, can we adaptively select planners to minimize the expected cost? So we call this the Blackbox adaptive planning paradigm. Here the role of the human designer is to create a library of planners we wish to train a meta-planner that takes as input the distribution of planning problems and adaptively selects planners from the library. We use the term black box planners because to the meta-planner, these planners appear to be black boxes, essentially that take as input the problem and produce the solutions. The contents of the planner are completely hidden to the meta-planner. So this means the designer has complete flexibility to create any sort of black box attempting to solve the problem. The question we are interested in is how can we train such meta-planners? So we first ask, how do we create a good library of planners? So it helps to visualize planners as performance curves. So on the x-axis are different planning problems, and on the y-axis is a score that goes from 0 to 1, which is simply 1 minus the normalized cost. And each planner is a performance curve. So we can begin by populating the library with different state-of-the-art planning algorithms and selecting some reasonable planners. And we call such planners general purpose planners because while these planners can solve a large number of problems, they don't really overfit to any one particular class of problems. Right? So, so this results. So as a result, while they have a good performance or a good large support everywhere, on a very few small fraction are they within epsilon of 1. However, what ends up happening is you have clusters of planning problems where no one planner does well. So we can design customized sampling techniques. So you can think of narrow passages as one such cluster. And we can come up with customized sampling techniques to solve only such problems. And we call such planners precision planners because while they solve a small fraction of problems, they have a high score on the problems which they do solve. In other words, they are overfitting to these problems by design. So in this way, we can create a library of planners that has sufficiently good coverage. So let's see the difference between these two classes in an example. So we have a UAV flying around in an environment with convex obstacles. Since the space has good connectivity, general purpose sampling based planners does well on most of these problems. But on a small set of problems shown in orange, the general purpose sampling planner is not able to focus in the right homotopy because it's sampling everywhere. But for such problems, we can design a precision planner that focuses its sampling in this yellow volume and is able to find a path through the gap to reach the goal. Okay, so now that we can create a library, let's return to the main problem. We want to design a meta planner that takes as input a planning problem, extracts some context about the problem, and then selects a planner from the library. The objective is to maximize the expected score. And notice that we can frame this as a cost-sensitive classification problem. However, there is an inherent difficulty when it comes to selecting a single planner. So consider this case where planner 1 is a precision planner and planner 2 is a general purpose planner. So for a given problem, the precision planner focuses its search in a volume and is able to quickly find a path. The general purpose planner finds a poorer path. But if we slightly change the problem by shifting one of the obstacles, suddenly the precision planner is not able to find a path, while planner 2 still finds a solution. Now, both these problems may map to the same feature vector, but with completely different labels. Right? So this makes learning particularly challenging. Since predicting a single planner is difficult, our key idea is to predict an ensemble of planners. We can then run this ensemble in parallel and take an argmin over all the solutions. This is a very powerful attribute of motion planning because we have a crisp evaluation function to rank different solutions. This implies that we can hedge our bets by predicting a diverse list of planners such that at least one of them has good performance. So the question is, how do we train a list of predictors? So let's try to understand this in a simplified setting. We have a library of planners. Consider a planning problem distribution that's uniform over this interval. We want to select a static list of 3 planners that's maximizing expected performance, where the performance is the maximum score of a planner in the list on a problem. So this is a combinatorially hard problem, which means to get the optimal solution, we would have to explicitly list down all combination of 3 planners and compute their expected performance. However, we will see there's an efficient way to solve this problem. So consider the following algorithm of greedily selecting a planner to maximize the expected gain in score. Right? So the first planner we would select is the one with the maximum area over the interval, which is planner C. The next planner we would select is planner B, and the planner after that is D. So we end up with a list that has pretty good score almost everywhere, and there's a theoretical guarantee for this. The performance function turns out to be a monotone submodular function, which means that it has diminishing returns. As a result, Cross et al. Shows that for such functions, a greedy algorithm is near optimal. So we exploit this property by proposing to train a list of predictors by stacking cost-sensitive classifiers on top of each other. So the way we do this is that the first predictor is trained on all of the problems. So we end up with two classes of problems, solved problems by predictor 1 and unsolved problems by predictor 1. And predictor 2 is only trained on the unsolved problems, and this process is repeated, so deeper predictors focus on the unsolved problems of their predecessors. They apply the submodularity property to show that training such a training procedure actually leads to a near optimal sequence of predictors. So we evaluated our approach on a spectrum of planning domains where we are either selecting different seed trajectories, different heuristic strategies, or different planning strategies. And in all these data sets, we showed that for various learners and losses, the ensemble prediction leads to a significant reduction in empirical risk. So we now return to the result we showed earlier, where UAV is flying for long duration outdoors. Let's take a closer look at the training and test procedure to get some insights behind its success. So during training, we create a database of 1,000 worlds by creating a map of the environment and randomly sampling start and goal locations. For the purpose of this test, we use a small library of 4 general purpose planners and 4 precision planners. These precision planners are created by using some custom bottleneck sampling strategies. The ensemble size is 2, and we discover many edge cases in the training data. So these are cases where, say, the goal location is too close to an obstacle, rendering general purpose sampling-based planners kind of ineffective. But our precision planners are particularly suited to solve such problems. So let's take a look at a snippet of what happens at test time. So this reel shows different planners selected at different time steps. So let's zoom in on one portion. And we can see that since this problem is a conventional problem, the meta planner selects one general purpose planner, bit star, which is actually able to solve this problem easily. But if we zoom in on another portion of the test, we encounter an edge case where the goal is too close to the pillar. So the meta planner appropriately selects precision planners, one of which solves the problem. We also showed closed loop evaluation on another platform, a smaller quadrotor. So the sensor range and reaction time of this platform is very different. We flew this UAV in different situations, such as avoiding a mound here on the left, or avoiding planning around some trees on the right. And again, the meta planner is able to appropriately switch planners to deal with both these situations. So we answered the black box question by proposing to greedily train a meta planner that adaptively selects from an ensemble. So we now zoom back inside the planning module and in fact treat it as a white box and ask whether adaptation can be applied inside the planner to learn policies. So in this paradigm, the human designer creates a white box planner with a tunable policy. The role of the policy is to make planning decisions, observe outcomes, and infer details about the problem. Such policies can be heuristic. In search-based planning, they can be sampling policies or collision checking policies. The question we are interested in is how can we train such policies efficiently? So let's start with the problem of learning a heuristic policy. So in search-based motion planning, an algorithm grows a search tree of feasible robot motions from a start configuration to a goal configuration. This is done incrementally by expanding leaves of the tree, and heuristics are policies that decide which node to expand. Hence, they're critical in ensuring real-time performance by trying to minimize the number of expansions to the farthest from. There's a large body of work in trying to compute heuristics that goes all the way back to the 70s. So in the context of planning, heuristics have often been viewed as the distance estimate of the cost to go. So both relaxation-based approaches as well as learning-based approaches have been employed to compute good heuristics. However, these methods overlook a fundamental limitation, that a small estimation error in this distance estimate can lead to an excessive amount of expansions. So consider the following case where we are planning in a world with a cul-de-sac. This is also referred to a bug trap in planning literature. A commonly used heuristic is the inflated Euclidean heuristic to the Euclidean distance to the goal. And while that's effective in many cases, in this particular example, the search gets trapped in the cul-de-sac. However, if we knew that we were operating in a world full of bug traps, we should expect a policy to figure out when it's trapped and circumvent around the obstacle. So let's try to formalize this problem. We first define a framework in which we'll learn the policy. So this is the best first search framework. Here we have a search algorithm that's maintaining a set of 3 lists. An open list, which is shown by the yellow squares. A closed list, which is shown by the white squares here. And an invalid list, which is shown by these black squares. So at a given iteration, this search selects a node to expand from the open list. It then expands this node by evaluating outgoing edges.
I'll just put you on the speakerphone. Somehow the Skype doesn't connect.
Okay, so let's start by just going through best first search. So at a given time step, the search selects a node to expand. It then expands the node by checking outgoing edges. So it then expands the node by checking outgoing edges and updates all the lists. This process repeats till the goal is discovered. What we want to learn is we want to learn the select function, which we formalize as a heuristic policy. So a heuristic policy is a function that maps the 3 lists to a vertex to expand from the open list. And the objective is to minimize the expected number of expansions on the distribution of world maps the robot encounters. So note that this is a sequential decision-making problem where the decisions made by a policy at a given time step affects the input to the policy at the next time step. The uncertainty comes from the fact that the world map is hidden from the policy. So it's natural to view such problems as a POMDP, where we can define the state to be the open list and the hidden world map, the actions to be the node to expand. The one-step cost is 1 for all states until the goal appears. The observation is the outcome of the expansion, and the history is the set of all 3 lists. So one strategy to solve such POMDPs is use model-based methods like POMCP or Despot, but such methods require a lot of online effort, which defeats the purpose of having a cheap heuristic policy. The other alternative is to try model-free methods like Q-learning or policy gradient methods, but they are incredibly sample and inefficient. So our key idea is to get the best of both worlds by using imitation learning. Specifically, we train a learner to estimate the value of a given action, given the partial information encoded in the state of the search. And we train it by imitating a clairvoyant oracle that can fully process the world map, run backwards Dijkstra, and compute the optimal expansions to go. So on one hand, we are leveraging the oracle to discern good actions from bad. On the other hand, we are learning cheap policies that we can execute at test time. And we have shown this strategy of imitating a clairvoyant oracle to be quite general and useful in many other quantity problems, such as information gathering. Okay. So let's go through the algorithm SAIL that we use to train such policies. The algorithm proceeds in an iterative manner and has 4 simple steps. So step 1 is that we sample a world from the database. Step 2, we roll in with a mixture of the learner and the oracle to get a search state. In step 3, we randomly select an action, so a node from the open list. We then compute some features, so these could be local geometric features. In fact, they could also be a basis vector of hand-designed heuristic functions. We then query the oracle to compute the expansions to go for that action on the world map. So we then add the feature and action value to an aggregated data set, update the learner in a batch fashion, and repeat. So we can show by adopting analysis from Ross and Bagnell that such training policies leads to learned policies with nice performance guarantees. We evaluated SAIL on a data set of 2D planning problems to compare to a wide number of baselines. This table shows the average normalized expansions. We see that SAIL outperforms a host of learning and non-learning baselines in almost all these data sets. We also applied SAIL on a real-world problem where a quadrotor has to navigate through a maze of no-fly zones at high speeds. These no-fly zones reflect high-risk areas and can be quite complex in shape. So for such problems, when we apply a baseline approach of A star with a commonly used double heuristic on the problem, we see that it times out as it expands 1,910 states without progressing through the maze. But if we train SAIL on a data set of maze-like worlds, we see it's able to solve such test problems with only 180 expansions. It learns interesting yet simple techniques such as expanding states that are parallel to the walls, not backtracking once it's progressed through a corridor, among other things. We also did a flight test where SAIL was running on both the quadrotor, which had to avoid a no-fly zone maze at 5 meters per second. SAIL solved such problems on board the UAV within 100 milliseconds, which is far faster than any hand-designed baseline planners that we came up with. Okay, so we saw how we can train heuristic policies by imitation learning of clairvoyant oracles. We now examine a different role learning can play in planning, that of edge evaluation. So consider the problem of finding a feasible path on an explicit graph. So by explicit, it means we know all the vertices and edges of the graph and are free to evaluate them in any fashion. We wish to learn a policy that evaluates edges of the graph, receives an outcome, green when valid, red when invalid, and it continues till a feasible path is found. So in our application, the edge evaluation is an important computational bottleneck that dominates other planning operations. So hence, this must be minimized to get real-time performance. Prior work on this topic has approached this problem in 2 main ways, either by lazy methods, by lazily differing edge evaluation, or by modeling the C-space belief. However, these methods actually ignore a fundamental aspect of the problem, that edges in a graph are actually correlated. So for example, imagine a robot manipulating an object near a table. all edges that pass through the table are in fact correlated. Similarly, imagine a helicopter trying to avoid some power line. All edges that are intersecting with these wires are in fact correlated. So we are interested in actively evaluating informative edges that quickly collapse the uncertainty about whether a path is feasible. Let's try to formalize this as a feasible path identification problem. So we have a graph, G equal to VE. We have a library of paths on this graph, psi1, psi2, psi3, or up to psi m. The cost of evaluating an edge is CE. Our objective is to compute a policy that maps the history of decisions and outcomes to the next decision. So the next edge to evaluate. Think of this policy as being a decision tree that we're trying to learn. And the objective is to compute an optimal policy that minimizes the expected evaluation cost, such that when this decision tree terminates, at least one path is feasible in our library. So our key insight is this problem is actually equivalent to a well-known problem in Bayesian active learning, that of decision region determination, or DRD. We'll briefly talk about the DRD problem, but it helps to keep in mind the problem of binary search when thinking of this, thinking about DRD. So we have a set of hypotheses shown as these blue dots. The true hypothesis H star is unknown. We have a set of candidate tests that we can execute. Once we execute a test, we get a binary 0-1 outcome. We can use this to prune away inconsistent hypotheses. We also define regions on the space of these hypotheses. So these are shown by these dotted lines. And the objective is to find an optimal sequence of tests that drive the uncertainty into a region containing H star, while minimizing the expected cost. So this is roughly the DRD problem. We will now show how the feasible path identification problem is equivalent to the DRD problem. So imagine we can sample worlds from our distribution, where each sampled world is a candidate hypothesis. We can define a region as a set of worlds for which a path is feasible. So for all these worlds, path 1 is feasible. Similarly, for all these worlds, path 2 is feasible, and for this region, path 3 is feasible. Evaluating an edge is equivalent to executing a test. So depending on the outcome, we can, depending on the outcome of the test, we can prune out all worlds that don't agree. And the goal is to select an optimal sequence of edges to evaluate to drive the uncertainty into a region. This implies a path is feasible, and in fact, we can see the two problems are in fact equivalent. And that means that if we know how to solve the DRD problem, we can actually identify a feasible path. Turns out that the DRD problem is NP hard, however, but fortunately, Chen et al. Provide an efficient algorithm to solve this in their direct algorithm. Essentially, the direct algorithm defines a greedy criterion for selecting edges, selecting a promising edge to evaluate. Hence, it's very efficient. They also prove that this criterion possesses a property known as adaptive submodularity, which means greedy algorithms are in fact near optimal. So we use direct to compute a decision tree in polynomial complexity. But we run into a second problem. What if the world that at test time is not in our finite database? So we end up in a situation where the decision tree may terminate without finding a path. So we developed a DRD algorithm, bisect, to address this. Bisect makes a strong assumption that edges are independent Bernoulli random variables. So by making such an assumption, we are able to derive a near optimal policy that's closed form, that reduces complexity from exponential to linear. And since bisect can in theory handle all possible worlds, we execute it from the leaf of the decision tree to complete the problem and find the path. Okay, so we evaluated our approach again on a large number of data sets, from geometric planning, non-holonomic path planning, 70 nova-round planning. In all of these data sets, our approach is comparative with various learning and hand-designed baselines. So these are these numbers. Sorry, these numbers are the normalized evaluation costs. So all algorithms are normalized with respect to direct displacement, such that this right-hand column is zero. And also these are the 95% confidence intervals of the expected evaluation cost. Instead of mean and variance, I'm showing the upper and lower bounds of 95%. So so essentially 0, 0 means you compare it with the direct.
So higher numbers here are higher cost.
Yeah, lower means
better.
negative means you're outperforming the direct displacement. We now apply this approach on a real-world problem where a helicopter is avoiding power lines that are detected very late by the sensor. So we make the situation even more difficult, where we have wires and hills and no-fly zones that the helicopter has to avoid. So to solve such problems in real time, we kind of need to exploit the correlations between various obstacles that we see here. So the algorithm on the top is the baseline approach of using a lazy method to defer edge evaluation. So since such methods are not exploiting any correlation among edges, it ends up evaluating 590 edges before it finds the solution. On the other hand, direct plus effect is able to focus its search just above the wire and to the left of these no-fly zones to find the path. So we saw how we can apply some active learning techniques to efficiently train edge evaluation policies, and now we have a completed picture. To briefly recap, we showed how we can use an expert planner framework to assemble real-time planners. We showed how we can, we then zoomed out and we discussed the Blackbox adaptation, where we showed how we can train a meta planner to adaptively select planners from a library of planners. We then zoomed in and treated planning as a white box and showed how we can directly learn planning policies using imitation learning or active learning. So that brings us to the conclusion and some open questions. So at this point, an apt question to ask then is which framework should we use, white box or black box? Right? So on one hand, white box planners are very efficient because we have a planner that directly adapts. In contrast, black box planners require explicit context extraction. They also require more human designer involvement to create a library. However, on the other hand, to have a universal white box planner, we need a very powerful planning policy. And this planning policy is also restricted to an underlying graph. In contrast, the attractive aspect of the black box planner was that or the black box paradigm was that we could handle edge cases by designing precision planners and hedging one's bet with an ensemble. So we make the following recommendations for unifying both frameworks. So it hinges on a key observation that white box planners are very effective general purpose planners, which means that we can train these planners on different subsets of the planning problem dataset to directly synthesize planners, which we can pool into a library. Then we can separately train a black box meta planner to select from such libraries. So the better the white box planners, the less is the burden to learn a powerful classifier. However, it's completely likely that we may end up in a situation where none of these white box planners are able to get us a good solution in real time. So this architecture still allows human designers to populate the library with their hand-designed precision planners, and we can leave it to the meta planner to learn an ensemble to decide which planner to use. So based on our experience over a vast set of based on our experiments on a vast set of platforms, we think this architecture is pragmatic and it preserves the attractive aspects of both the white box and the black box. Okay, so let's discuss some open questions that arise out of this one. So a historically hard problem in planning has been the issue of multiple resolutions. So this example is taken from Narayan et al., where they show a PR2 that has to go from a corridor through a door into a room, holding a board. Now, solving such original 12 Drd problems in real time is completely hopeless. But we can clearly see there's a lot of low-dimensional structure to the problem. So, for example, to get to the door, we only need to reason about the base position. And in theory, we should be able to learn such structures automatically from data and then let conventional search techniques plan with such representations. A second direction would be to venture beyond motion planning. So the ideas we discussed in this talk were very general and should be applicable to historically hard problems such as belief-based planning. In fact, we have some work on learning information gathering policies using the imitation learning techniques that we discussed here. And finally, no matter how good a learner is, the planner is eventually going to fail. Even if such failures are rare events, once the robot fails, since it can't teleport, it's going to experience that failure over and over again. It would be interesting to import techniques from online learning into this framework to learn from experience. In fact, in my thesis, we didn't discuss it here, but I showed how we can use algorithms from online paging to begin to address such problems. So we now conclude with a take-home message. We discussed today how real-time performance is critical in robotics, and planners have to adapt to the distribution of scenarios to achieve it. But that adaptation doesn't mean we directly need to predict a trajectory to use. Such policies are not likely to generalize very well. Based on the evidence that we've shown, it's much easier to predict options within the planning framework. The reason behind that is that it's okay to make noisy predictions, such as guessing multiple planners in the ensemble, or expanding multiple potential nodes, or checking multiple edges, and letting the framework of planning to systematically process these predictions and arrive at a solution. So this leads to a very nice interplay between learning and planning, where learning is taking care of real-time performance and planning takes care of the generalization part. And I'd like to acknowledge the folks who played a critical role in this thesis. I'd like to thank my advisor Sebastian, my thesis committee, Sid, Marshall, and Ashish. It's a Drew who was on my qualifier committee. I'd like to thank all members of the Air Lab who played a critical role in helping me complete this work. I'd like to also thank all collaborators outside of the lab who co-authored on the papers I presented today. With that, I would like to take some questions.
So I think we'll start with a couple of rounds of questions of the committee and then open it up. So I think maybe Ashish should go first.
Ashish? Yeah. Yeah. Yeah, so this is like a Q&A section, just go ahead. Ashish, could you hang on a second? Yeah, go ahead. Sorry, we lost you for a second. Yeah, go ahead. Okay. Okay. Thanks. Yeah. Ashish, sorry, go ahead. Yeah. So just to repeat your question, you're asking about adversarial scenarios? Okay, so Ashish's question was how can we adapt to adversarial scenarios? So by adversarial, do you mean where obstacles are placed in like pathological kind of cases? entirely sure if worst case would give the behavior we want. I mean, think of RT Connect, an algorithm like that, which probably would be able to find a feasible path for most of these problems. But it would have a very poor performance on average. Right? So if you're only optimizing for the worst case, we might end up with undesirable behavior. And historically in machine learning, people deal with this worst case problems by kind of weighing the samples differently and still using the empirical risk minimization paradigm, but maybe upweighting samples. So maybe or techniques like mining for hard problems. So that's how I would deal with it. So if for example, if there's a particular example that that's very important and I care about, I would try to outweigh the importance of that problem.
Thank you very much.
Sid?
Oh yeah, you should. Oh yeah.
Oh, sorry. Yes. Go ahead. Sorry.
So I just had first of all.
Sorry, Marshall's going ahead. He has to leave.
So you're making trouble, Yancy. Yeah. So first of all, great work, very comprehensive work. So I have 3 questions. The first one actually I think is related to that question on the sale. Technique, right?
Yeah.
So you train this on a family of work.
Yeah.
Right. Now, if the actual world is far from that training family, you can get an arbitrary bad policy.
Right.
So I guess it's kind of the same question as differently. You know, how do you deal with it? First of all, do you train with different family of words?
Yeah. So there's a caveat to that. If you take all possible words and pool them in one gigantic data set and try to learn a heuristic, you will not learn anything anything good.
Exactly.
That was very counterintuitive intuition where it was better to actually learn heuristics for maze-like words and then maybe a different heuristics where you have these bug traps. Fusing them led to a poorer performance.
Yeah, but in practice, that's what you actually do. In other words, you have multiple distributions.
Yeah.
You learn a different policy for your distribution.
Yeah.
How do you choose the distribution? How do you know that's a good coverage?
Right. So for my cases,
That
these
seems
were,
to be another NP hard problem on top of it.
Yeah, that's definitely. This is in these experiments. This was just using some domain knowledge to kind of cluster these problems. But that's an interesting question.
That seems to be related to your comment that you made in the Blackbox presentation, the first one, about the special versus general.
Yeah.
That's kind of the same thing, right? You can probably turn a policy for general cases, the average maze. Exactly. But then for the narrow passage, you need a very special.
Yeah. So interestingly, what at least from some preliminary experiments, what I observed is it's hard to explain why, but it's better to say train 2 policy on these 2 clusters and actually learn a classifier on the front end, like a black box classifier that's just choosing between the 2, rather than have one policy that's inferring.
But so my question is, so then the question is, do you have any thoughts on how to decide on how many policies you need to train on which subset? So you could imagine trying to train a policy on that large set of words, discovering that it gives you a bad policy, and then splitting it.
Yeah.
Okay. Yeah. How do you split? How do you even detect?
Right. So the tricky part of the splitting is that it's actually tied into your learnability, right? What is learnable? It's dependent on your policy class. So you would have to have some sort of iterative process where you maybe train on a small subset, see problems on which it's performing, and then maybe use that data set to augment it. That's how I would go.
So on the DRD dissect thing, I still have that question.
I can explain.
There's something I'm still confused about. So what it's really optimizing is the number of edge tests, right?
Yeah, number of edge.
So all it guarantees is to find a feasible.
Yes.
The path could be really, really bad.
Yeah,
in terms of cost.
Yeah. There's a reason for that. So we use the library of k shortest paths.
Yeah.
And we say, if any one of these k shortest paths we find is good enough. We just want to find one feasible path. So we have a bound in that way.
Okay, so it's not quite as bad, like you said, arbitrary.
Yeah.
Okay. Oh, I see.
So it's not
guaranteed to find a feasible path.
No.
That's not the one.
No, it's trying to find a bounded.
Find one from the library.
Yeah, one from the near optimal set.
Yeah, I see.
Sid, go ahead. Sorry.
Thank you.
Yeah.
Sorry, I had to kick out of my conference room.
Yeah.
Thanks. That's really fantastic work, and having been part of it from the very beginning, it's really exciting to see the progress. And looking forward to having you here at the University of Washington very soon, where it's nice and warm and a little rainy. Now that we've gotten all that away.
Yeah.
So I had one sort of higher level technical question, and maybe specific questions that we can talk about later that we've already talked about a bunch of.
Sure.
And maybe this sort of echoes a little bit of what Marshall was saying. As I was listening to you talk, I was wondering, when you're learning, let's look at the heuristic learning component of it. As you're learning some heuristic and implementing it in an environment, as I was watching some of those, it's just being evaluated, or the search tree growing, I knew that something bad was happening because you're an expert observer watching that.
Right.
And so at that point, I was wondering, is there a way to incorporate interactive imitation learning into this framework? So there's obviously Dagger style algorithms which demand not just demonstrations from a user offline, but actually demand interactivity during the process of execution. But can you envision ways in which an expert operator could actually coax the search, move in different directions, and use that coaxing actually to learn online? I know you were referring to this while you were talking of if the system does reinforcement learning style updates of introspecting its own performance in terms of the number of edges that it actually ended up evaluating,
Right.
and updates its heuristic space development. Can you think of it in the imitation learning framework?
Right. I mean, so interesting. I mean, there's definitely a way where we could, if we could set it up in this fashion, where we are, I guess, querying an expert for. So it's very difficult for an expert to say, what should be the optimal value to go for a particular action, right? But if an expert is good at ranking, like historically, an expert can say this expansion is better than this expansion, right?
Right. It's also possible for the expert to give a 0-1 loss, right? Like you could say, like, look, you're going into a bad area.
Sure. So yeah, definitely. And one rough way to do it would be to maybe initially train a policy using this method, so we at least get a reasonable policy that's using the sale algorithm that I showed, and then maybe to now turn that into this paradigm where the policy is is giving the expert what decision it would do, and the expert is kind of ranking. I would prefer this over this, and so and then we are essentially continuing to train the policy based on this feedback. That would be one way, but I think there's a difficulty in choosing which. I mean, for an expert to look at all the history of expansion seems very laborious. Like that could not possibly scale. So in what form of feedback should a human be allowed to give is an interesting question. Because based on that would drive how we use that feedback, right? So, for example, if the human if the system could actively provide some queries to the human saying, is this a good expansion or is this not a good expansion? Maybe that could be used. So that's an interesting question.
And then one sort of final question would be, and I think Marshall alluded to this question too, which is, the Bayesian DRD framework that we have essentially works on K paths.
Yeah.
Right? I give you K paths, and then you can come up with the decision tree to actually evaluate them. And can you talk about how you
Right. So I mean, there are different ways. I think so for example, an example way that we've talked about before is where you start off with a library of k-paths, run this algorithm, then refresh the library with k shorter paths and keep going. And at least we know that algorithm will converge with you having found the optimal path, right? Because you're forcing it. But there's this. But in such a paradigm, it's really difficult for one to control the rate of convergence. You're just relying on the algorithm to figure out. You're essentially not explicitly specifying this the tension between finding feasible paths with little effort and finding the optimal path, right? So incorporating that. So if you were to try and incorporate that, maybe we would have to look at other metrics that's kind of explicitly trying to balance solution cost with planning effort. Like for example, the way Chris formulated his utility guided planning, where he's explicitly balancing planning effort and solution cost, and then using that criteria to guide the collision checking policy. But yeah, that's how I would think about that problem.
Thank you.
Okay.
So you talked a lot about planning distributions and basic distributions of where an algorithm can solve a problem. Do you have some intuition on how you can actually formalize this, express it in a good manner?
It's a very difficult question. So I'll actually show you one example of why it can get very difficult. So this is an example when we were working on hybrid, on the Rabbit Star paper, when we were working on hybrid local and global search. We thought for sure that doing local and global search would just outperform every algorithm there is, right? And that's true in R8, so the green line shows our algorithm that's outperforming all the baselines. But in R2, we had trouble to outperforming the bit star algorithm, no matter what we did. It just turned out that the pure virtue of random sampling, rather than judicious invocation of a trajectory optimization, was better. And this flipped from R2 to R8. And so I guess to answer your question, the answer is very intricately linked with dimension. It's not as obvious to look at an algorithm and say that this would work in this scenario. It's something that you would have to empirically find out.
And then some other question on this. Define these as precision and general plan. General purpose. And so the computational cost of these is going to be different, right? So could that factor in somewhere in these budgets, or how would you?
So the way we define it is we are saying we're going to give everyone a same real-time planning budget, so everybody gets a second of planning time, and whatever is the cost of the solution that you can produce in this real time is the cost of the plan.
Right, but like one precision planner could be just produce a single trajectory in the millions of the second.
That would be a waste. I feel like it's not user.
Right. So I guess the question is like, where do you you shift some of the computational complexity from the planning algorithm into the selection of the algorithm, right? So you're switching. Like if you have a million precision planners, and then your planner would be choosing.
Right. So the competing paradigm to selecting and running a bunch of stuff in parallel is to have this complex if-else decision tree, right? If run this planner doesn't work, or progress not good switch. But the problem in that second paradigm that you're referring to is that you have it's very hard to look at the look at a search tree and say if the planner is close to being done or not being done. Especially for the precision planners, because they are doing some bias sampling, and so once samples perfectly aligned, suddenly a solution is found. So predicting that either algorithmically or even with a machine learning technique is really difficult, which is what motivated us to actually switch to this running planners in parallel and giving them the full budget.
And then the last question, and maybe you kind of already answered this here, but this kind of degradation as you're planning, like your training distribution shifts, is this, do you see this more as a step function or a continuous thing, or what's
what do you mean by
so basically you train on some set, you test on some other set, and that set could be almost the same, or it could be further away. Like for example, you showed this training example of this almost like container city, which was similar to where some of these other tests were done, but then if you test Cascola or some other hills, then
So it's not exactly a step function, because usually the ensemble, say if I have a budget of 3, the first element in the ensemble is usually a general purpose planners, which have an implicit generalizability. So it's only in the later terms in the ensemble do we see precision planners being selected, which are very finicky. They would probably not generalize. I mean, they are overfitting by design in some sense. But so there is a robustness to distribution. I would say because of that general purpose planner, it's still doing something complicated.
Ashish, do you have more questions?
No, I think it's fine.
Okay. Any questions?
I had a question in the imitation learning part. So you have Oracle which is giving you sort of a heuristic that, okay, this is the cost to go or something? But if you're, I think it was something that Marshall asked as well, that if you have your words which are very different, those heuristics can be, while training, if your words are like, this is like a C-shaped obstacle, if you have a narrow passage, that heuristic that the Oracle gives is very different. So do you just train on separately on specific types of obstacles, or?
This is going back to the point Marshall brought up, is that we initially would train on these parametric distribution of worlds, like either mazes or certain combinations of these C-shaped kind of worlds. But when we started mixing, so creating heterogeneous distribution, it's not that the performance degraded. So it's the same as any machine learning. As long as your train and test distribution is aligned, it's fine. But I think it's the performance of a policy that's only trained on one homogeneous distribution is really, really good. So it starts suffering as soon as you make it heterogeneous. That was something we observed.
When you test, do you have a way of identifying what situation you are in so that you can use the information?
So, I mean, for our experiments, we only had a few such types of worlds, and we found it advantageous to train different policies on different, say, clusters, and essentially learn a classifier right on the mouth of all these different policies to quickly classify is it a maze-like world or is it a C-shaped kind of world, and that's not very difficult to do. I mean, they're fairly distinct. There's no subtle differences, so you can do that with very small features, very coarse density measures of the environment to classify what kind of world it belongs to.
In earlier part of your talk, you had this, basically you greedily selected the planners based on the score that they got, based on some set of problems. So how do you actually parameterize those problems? Because I think that parameterization is important to basically when
I'll just go to the training set. We're not. So are you referring to the training procedure here?
Yeah. So you have like set of problems or
Right,
you said.
right.
So how are
so
those problems parameterized?
So we are not so that was the previous example was just an illustration. What we are actually doing is we are training classifiers, right? So we're not parameterizing problems exactly. We're just training a list of classifiers. Think like a list of linear regressions or SVMs or random forests, right? So the first element of the list is trained on all the entire data set to do as good as possible on the classification problem, right? So to classify, to select planners that maximize the score. Then we train the second predictor in that list by looking at problems that the first predictor failed and greedily. So this second is only looking at the failure cases, and subsequently we are training a third one that looks at the remaining failure cases, right? So there's there's no explicit plan.
While execution or while test?
So while execution, we get a. I think it's helpful to look at this problem. So while execution, we get a planning problem. We are extracting some context. In practice, we use density estimates of the occupancy of.
So local or you assume that
Global. So we are like binning up the world at a very coarse level and measuring density estimates at different portions of the world. So that becomes a feature vector, and then we are then each predictor takes that context as input and makes a prediction, and that becomes our ensemble of planners. So each of these predictors take the feature vector as input and predict a planner from the list, and then we are executing all three of these planners.
Thank you.
Okay. In the direct plus bisect approach, so why did we need bisect? So and on top of that, bisect, you said bisect makes an assumption that each edge is an independent Bernoulli random variable.
Yeah.
It kind of goes against the motivation that edges are correlated.
Yeah. So the main reason we do that is because of this problem. That direct makes a realizability assumption that the world at test time is in your database. If it's not, the decision tree terminates without. The decision tree terminates at a step where it says the world is not realizable and I don't have a path. That's free. So we need to do something. So we need to actually reason about all possible worlds that may exist. Which means if you have E edges, all 2 to the power E worlds that may exist.
Yeah.
You need some algorithm that's that's complete, that will end with a path. And so what we do, so to solve that problem, we have to make some assumptions. We have to relax the problem. And one relaxation that works quite okay in practice is this independent Bernoulli random variables. So it works okay after the fact that we have already executed direct. So we've kind of collapsed the posterior over what worlds can be, and then we use that posterior, feed it to the bisect, assume each edges are independent. And the thing with bisect is it's really efficient. It's closed form, so you can just keep selecting edges until path exists.
Okay. And you have
and you have a performance loss obviously because you've stopped reasoning about the correlations. But I mean, think of it like this way: you're out of your training database, right? So nothing you can do about it.
Yeah, and the bound on the number of edge evaluations, is it from direct or is it from bisect? You said that you had a bound on the number of edge evaluations, right?
So it's from direct. Bisect also has a near optimality bound. It's on the cost. It's a near optimality on the cost, but it's also based on the bisect bound is based on this assumption being true. The direct also has its own bounds, composing.
So I have a very open question.
Yeah.
Let's say fast forward 10 or 15 years, right? Self-driving cars are done, and now the thing of today is self-driving, I don't know, personal vehicles. And then it becomes interesting, right? So now you can't ignore perception. So let's say you are Google and you have this insane database of people flying around. Mm-hmm. So then I think there are multiple options, right? Like, okay, do you learn costs over the perception area? And then you also have state estimate, you have some perception, certainty, maybe the definition optimality changes. So then, like, okay, what are the important problems according to you, and like, how do you even use all this database?
Right. Yeah, perception is very challenging, obviously.
No, I mean,
but,
I mean those, like, how do you integrate?
Yeah, I mean, if one way would be, if you were to preserve some of these ideas or carry them forward, one paradigm would be, as you mentioned, figuring out, good receding horizon planning problems, right? So perception comes in. Planning is a very nice tool that gives us these trajectories that the controller can follow. So maybe we want to preserve that. So then we would need to take this partial belief about the world from perception and learn some cost function. And this work from say Drew Bagnall's group on how to kind of take perception information and learn cost function. So once you have converted it into a receding horizon problem, you would still have to find a way to solve it. So some of these ideas would definitely be very important in that paradigm. Yeah, that's how I would.
Any last questions?
I have one comment to make. I have to leave in 4 minutes,
Okay,
so
great.
I guess to cut out and I can
Okay.
I can give you my virtual thumbs up now, but I can send some more comments.
Okay, yeah, definitely. Thanks, sir.
Okay.
Sorry about that.
No, no.